Thanks. So it's my pleasure to introduce Cam Macris. She's an assistant professor in earth sciences at IUPUI. And so she did a bachelor degree at Louisiana State University. And then she did a master and a PhD at UCLA in California. And after a PhD at UCLA, she come for doing a postdoc at Caltech. And that's where we overlap actually briefly for a few months. She was starting her postdoc at Caltech when I was finishing my first postdoc actually over there. And then she has been hired as an assistant professor at IUPUI, which is a part of the School of Science, which is part of Purdue University. And so she has been there over there, and she has been very successful. She has actually developed this whole new experimental setup that she's going to present today, and which I'm very excited to hear about, where she has actually levitating lava. So I'm really excited to hear more about this particular technique. And so she's here today to present as part of the 2021-2022 Mineralogical Society of America Distinguished Lecturer Program. And I have to say also that she's the first of the Peter Busak Distinguished Lecturer. So she's the first Peter Busak Distinguished Lecturer, which is basically a lecture series that is promoting the new direction in mineralogy and petrology. And that's what she's going to talk about today, with presenting basically this very new and innovative way to think about planetary science. So thanks again, Cam, for being there today, and I let you go.
Okay, great. Thank you so much, Sarah, for that really nice introduction. I'm so happy to be talking to you all today. I wish that I was there in person, but I'm very glad to be able to share my research and hopefully get to chat a little bit after the talk if people can stay after. I think I heard that you have a little time afterwards to hang out. So I'm going to share my screen. I'm also going to, there are some times when I'm going to ask for a little bit of participation. So get ready to maybe write some responses in the chat or use your thumbs up. So hopefully we can have a little bit of interaction and have it be a little bit more lively. Okay, I'm going to share my screen. Okay, can somebody confirm that you are looking at my slide and only my slide?
We do.
Great. Thank you so much. Okay, so the title of my talk, as you may have already seen, is Laser Beams and Levitating Lava Orbs, Science Fiction or Real Tools for Studying Planetary Science. Before I get started with the science, I wanted to tell you just a little bit more about me, because normally I would be there and I would be able to meet with people and get to know you, and you get to know a little bit more about me as a person. And so I thought I'd just take a minute to share a little bit. So my name is Catherine Macris, and my initials spell out Cam, and that's why everybody calls me Cam. So please do call me Cam. My pronouns are she, her, hers. I'm a first-generation college student. I was a federal aid recipient throughout college. I'm publicly educated, K through 12, and I'm the first and only graduate student in my family. The picture that I'm showing here was a very proud day for me. This is the first PhD student who received his doctoral degree in my group. This is Dr. Rigwang Pan at our commencement ceremony last summer. I'm also a dog mom. I took this photo this morning of my dogs who are on their cozy heated bed because it was 10 degrees. I'm very passionate about science communication, so I'm really very excited to be giving this talk today. And also, I really believe that earth sciences should be welcoming and accessible to everyone. So let's get to the talk, and you can learn more about my research. So I'm wondering, when you maybe read this title of this talk, what did it make you think of? So Now's the time for putting some things in the chat. I'd love to hear just what picture came up in your mind when you heard this. Laser beams and levitating lava orbs. And I'm going to bring the chat up so I can see. I see lava in the sky. LAICPMS. Oops, I don't want to do that. Okay. Something from Star Trek. Lava lamps, Dr. Evil. Okay, these are great. Great answers. So what you might have thought this talk was about, if I was going to guess, what did I think you would think? So you might have thought of lasers. You might have laser cat specifically. You might have pictured something like this, where there's a laser beam and then there are some levitating orbs around. You might have pictured something like this, which to me sort of looks like some magma ocean planet, but maybe it's very tiny and levitating. Maybe you just thought of lava. Maybe you thought of something very science fiction-y, which I think somebody said something from Star Trek, so I'm not too far off at my predictions. So what this talk is actually about, we're going to talk about asteroid impacts. We're also going to talk about molten rock and its interacting with gas as it is moving. So interacting with a flowing gas. We're going to talk about how geochemists work in the lab to learn things about how planets form. We are going to talk about lasers, and we're going to talk about levitating lava orbs, which is basically what you're seeing right here. Can you see my cursor when I do this?
Yes.
Okay, great. Okay, so one of the terms that I'm going to be throwing around a lot in this talk is impact event, which usually refers to a meteoroid striking the surface of a planetary body, which usually results in an impact crater. So, and oops, I wanted to restart that animation really quickly. In other words, a space rock crashing into a planet and making a hole in the ground, as we see in this animation from NASA. So just some fun facts about impacts, or IMFACts, if you'd like. On a daily basis, about 100 tons of space dust and sand-sized particles bombard Earth's atmosphere. So what that means is that if you ate your lunch outside today, you probably have some stardust on you. This stardust is everywhere. You can prove it to yourself by sweeping up all of the dirt on a flat rooftop and using a strong magnet to separate the particles that contain metal. Some of that magnetic stuff is probably micrometeorites. These tiny rocks from space are the oldest known stuff in the universe, and they're the building blocks of planets. So this is a little micrometeorite, and this is a blown up picture of it. They're very beautiful. About every year or so, an object the size of a building might penetrate Earth's atmosphere. This would produce an impressive fireball, but likely would be burned up and broken into small pieces before it reached the surface. So an example of this kind of event was the Chelyabinsk fireball in 2013. So this is coming on 10 years ago now, but I think some of you might remember. This was popularized because it was captured by a lot of Russian dash cams in videos like the ones that I'm showing here. About every 5,000 years or so, something the size of a football field would penetrate Earth's atmosphere and hit Earth, and this would cause some significant damage. So an example of this kind of event occurred in 1908 in Tunguska, Russia, which is in Siberia. So if you remember this, I'd be very impressed. And this is a headline, or a news article from that time that I'm showing here. Many Russians, believing this to be a sign of the approaching end of the world, left their homes and belongings and wandered off to holy shrines and monasteries. So this was pretty dramatic event. Every million years or so, an object large enough to threaten Earth's population might strike. And so an example of this would be the Chicxulub impact in Mexico. So this is showing the location of the Chicxulub impact crater, which is buried beneath sediment and water in the Yucatan Peninsula. And this is the event, of course, that is linked to the extinction of the dinosaurs. So evidence of these impacts can be seen by just looking up in the sky on a clear night at the moon. So we can see there are scars visible on the moon, and also these other rocky solar system bodies as craters that formed as a result of past impacts. And we can't really see any on this image of Earth, but that doesn't mean they're not there. There are about 190 currently documented impact craters on Earth, shown as these red dots, versus thousands or tens of thousands on the moon. So why are there so few on Earth compared to the moon? Again, why don't you put your thoughts in the chat? Why do you think there are so few craters on Earth identified relative to the moon? Erosion, yes. What else? Impacts in oceans will be less evidence, yes. Atmosphere and wind, plate tectonics, tectonics and surface processes. Yes, you're all right. That's exactly right. So some craters are easy to find. So here's an example. This is Meteor Crater or Barringer Crater in Arizona that some of you may have seen. Give a thumbs up if you've seen it, if you've been there. This is a massive hole in the ground. It's hard to miss, okay? And then compared that to the Chicxulub crater that is covered with sediment and water. So this was only discovered by geophysical surveying in the 70s. So yes, there are a lot of forces that can destroy or hide craters. So let's talk a little bit about why we care about researching impact events. Impacts are responsible for the formation and evolution of Earth and other planets. So as rocks in space impact each other, they accrete or grow over time, which is how planets are built from scratch. A lot of impacts kept a young Earth very hot enough to differentiate or to separate into a metallic core and a silicate mantle. And then also a very large impact resulted in the formation of Earth's moon. Impacts also play a role in altering Earth's composition. The young Earth was continually bombarded by space debris, which produced enough heat to completely melt it, as I said earlier. And in this state, it might have lost some of its initial chemical constituents as some material was vaporized by the extreme heat. Volatiles, this word here, are chemicals or isotopes of elements that can more easily be converted from liquid to gas. And these could have been lost, or some of them. And this process would help explain why Earth's composition is slightly different than meteorites. Impacts have also played a role in life on Earth. So comets and meteorites are thought to have delivered water in the form of ice and other important ingredients for life to a cooler Earth. And large impacts can also trigger mass extinctions, as in the Chicxulub event that I mentioned earlier. And so this dinosaur is sad because all of his friends are dead. This is an actual book. You can buy it, but I would not recommend buying it for your child. So he's sad and he wants to know all of his friends are dead, but how? So there are still open questions as to how impacts cause such an extinction event. So for example, how much of it is a direct result of the impact's immediate devastation to the local and global environment versus the longer lasting after effects that we think are associated with large impacts. So let's talk a little bit about how we research impact events. Well, as we learned earlier, large impacts aren't occurring very frequently on Earth these days, so we can't observe them directly, luckily. Although that hasn't stopped Hollywood from making science fiction disaster movies for decades and decades. And here's just a selection of some of the movie posters from movies about impacts on Earth. My personal favorite is Night of the Comet. This is a very old one here. People probably have seen Don't Look Up recently. I'd like to, if you would share your favorite impact movie in the chat, so we can all talk about that later. They're all bad. All right, so how do we research these events? Well, one way we can study impacts is by using powerful computers working in parallel clusters to make simulations of impacts using complex and computationally expensive models. So this is an animation that I'm going to show here of such a simulation. Every time the screen blinks, what's happening is that it's changing scale. The X and Y axes are changing scale. So this is helping us to visualize what happens during and after an impact event, and we can use it to make estimates about things like the temperatures of the explosion and how much rock would be melted and displaced by an impact. These simulations take so much computer power and time that they tend to keep them pretty short, leaving a lot of the process unexplored. Another way we can research impacts is by studying the products left behind by ancient impacts on Earth. So these include craters and also something called tektites. I really like this artist's rendition because it shows what appears to be hot and molten material being ejected away from the site of impact. And this is the stuff that eventually becomes tektites. In this slightly more scientific cartoon, we see that as a projectile impacts Earth's surface, its kinetic energy is transferred to the crust in the form of intense heat and pressure, resulting in fracturing and metamorphism of the underlying rock, as well as melting and vaporization of the upper layers of the target material and the impactor. And then this material is going to be immediately ejected away from the site of impact, shown by the arrows. Oops, sorry, I went backwards. Here, I've superimposed a crude visualization of the impact ejecta, which is an expanding plume of molten and vaporized rock, and we call this the impact plume. So this powerful plume pushes aside the ambient atmosphere, which allows the melt ejecta to follow long ballistic paths while still entrained in that hot gas, that vaporized rock, which keeps the melt hot, allowing enough time for aerodynamic shaping. So at some later time, the plume collapses or dissipates, causing the molten material to cool mid-flight into a glass. And then it later falls to the ground and we find them and we call them tektites. The formation and evolution of tektites are determined by a number of factors, some of which are listed here. But what we are going to focus on in this talk are the vapor melt interactions in the impact plume. These impact plume dynamics are the least well understood aspect of the impact process, and yet the very thing that may have the most devastating effect on the local and global environment. And we can learn about the impact plume by studying tektites, which experienced it directly. They were present at the scene of the crime, if you will, and they can act as eyewitnesses of sorts, recording information about the plume even after it dissipates. So if we ask the right questions of them, they may be able to tell us about some of the plume conditions, for example, such as the heating times, durations, and maybe vapor pressure in the plume. So earlier I told you that there are about 190 impact structures identified on Earth. There are only 4 currently recognized major tektite strewn fields around the world. There's the North American, Central European, the Ivory Coast strewn field, and then the Australasian strewn field, which is by far the largest and also the youngest. And as these are shown on this map, a dot represents where the crater is. And then the enclosed shaded area is where the tektites are found. So you might notice that there's no dot over here for the Australasian strewn field. The impact crater has not been definitively located, although a 2019 paper by Sia and others thought that they identified through gravity data that it may be beneath the Balavan volcanic field in southern Laos. This is a different projection of the Australasian strewn field. So now it's shaded in green, and the red symbols are showing places where tektites have been located at the time that this map was made. There are several different tektite forms, morphologies that are found in this strewn field. There are what we call layered tektites, which are large chunks. There's maybe the largest one is like maybe a loaf of bread. And these are thought to have cooled in puddles on the ground. There are also splash form tektites, which are finger to fist size. And these are the ones that cooled mid-flight and have these aerodynamic shapes. And then there are microtektites, which are basically little mini splash forms. And they're thought to have cooled from much smaller melt droplets. And in some cases, even may have recondensed from vaporized rock. By studying some key features of these glasses, we might be able to have a better understanding of the impact plume and also get some clues about the tektite formation process. But first, we need to know how different temperatures and heating times affect tektites. And so that leads to the third way we can research impact events, which is in ultra-high temperature experiments. So we can reproduce the extreme temperatures associated with impact melting in an aerodynamic levitation laser furnace. On the right is a photograph of the aerodynamic levitation laser furnace in my lab. And on the left is a schematic representation of its parts and how they work together. So in this apparatus, a small spherical sample is freely floated on top of a vertical gas stream while being heated with a CO2 laser. The temperature is measured by a pyrometer, while the laser power and gas flow are controlled by a LabVIEW program. The action is all happening behind this welder's glass and inside the chamber here, which you can see in this photo. We can use a variety of gases for levitation, such as those that are listed here, and even mix them to create different environments for experiments. And the gas is what allows the sample to float above the nozzle while being heated. And this is what it actually looks like. So there's your levitating orb of molten rock right there. So what's happening here is an example of Bernoulli's principle. And this is the same principle that allows airplanes to fly in the air. And it's what allows this ping pong ball to float as this person is blowing air through a straw. So you could actually do this yourself if you have very good, strong lungs. I can't do it, but one of my students who played the French horn could do it. So the fast air moving around the sides of the ball is at a lower pressure than the surrounding stationary air, allowing the spherical object to levitate in the lower pressure region. And this is what is happening in the melt spheres in our experiments. So with this technique, we can perform what are essentially containerless experiments. So this way we can avoid any interactions between our very hot sample and a container, which could compromise the experiment. Also, many crucible materials would melt at the temperatures we regularly achieve in these experiments. The technique also has a bonus feature for studying impact melts because it involves high temperature melts surrounded by a flowing gas, which is relevant to conditions in an impact plume. So I'm going to tell you about two studies we've done so far using the levitation furnace to study impact processes, or I should say two that are published. In the first study, we used diffusion in tektites in ultra-high temperature experiments to estimate thermal histories of individual tektites. In the second study, we determined the stable isotope fractionation of copper due to partial evaporation of melts in ultra-high temperature experiments. And both of these deal with vapor melt interactions in the plume, and we will talk about how. Let's start off with this diffusion study. Here's a photo of one of those Australasian splash form tektites. It's been cut into slabs. So this slab was cut out of here, and this is it laying on its side. And now I'm showing one of these slabs magnified so that we can see some of its features. And then there's a scale bar here. This is just a transmitted light photograph. And the majority of this glass is homogeneous with a roughly rhyolitic composition, as we can see on this plot of silica versus alkalis. So rhyolite field is over here. Here are tektites. We can see that tektites are more depleted in alkalis than obsidian. Entrained in this felsic matrix are some local heterogeneities. So I'd like to point out these tiny little blebs speckling the surface. These are almost pure silica glass, so just SiO2. They're called Le Chatelierite, and these were once quartz grains that were melted by the heat of the impact, but did not homogenize with the rest of the melt. Then it cooled and they sort of froze into these little silica glass blebs. There are also these flow bands, as you can see here, called Schlieren, which are intermediate in composition between that felsic matrix and the pure silica inclusions. So now what I'm showing is some backscattered electron images taken on a scanning electron microscope. And these are all different Le Chatelierite in one tektite. So the dark gray is the Le Chatelierite, or the pure silica glass inclusion, surrounded by the felsic glass of the tektite. And the scale bars are all 100 microns here. So these all are varying in terms of size, shape, and degree of vesiculation. But what they all appear to display are, there we go. What they all appear to display are these diffusion halos at the inclusion host glass contacts, which are this sort of intermediate in grayscale area between the Le Chatelierite and the matrix glass that I'm pointing out with the gray arrows. So this indicates that silica was diffusing away from the Le Chatelierite into the felsic melt while the sample was molten at high temperature, and that the melt was quenched to a glass before it could homogenize. So these backscattered electron images are like snapshots in time, and we can potentially extract information about the thermal history of this sample using these compositional gradients. So let's just take a minute to talk briefly about the diffusion process so that we're all on the same page, because some people might not think about this a lot. So in this cartoon here at the top, we are looking at a panel at time equals 0. We have two distinct compositions with a sharp boundary between them. At some later time, we see that the particles are migrating from places where their concentration is high to places where their concentration is low. In the bottom panel, at some much later time, the particles have reached equilibrium and are totally mixed and homogenized. And then these cartoons next to those panels are showing the same context, but in the same concept, but in the context of a pure silica melt diffusing into the surrounding felsic melt, as in our tektites. This behavior is dictated by Fick's first law of diffusion, which states that diffusing mass transport depends on a component's concentration gradient, del C, and its diffusivity, or diffusion coefficient. This can be thought of as a measure of a component's mobility and is going to vary with things like temperature, pressure, and composition. And this can be used in applications as a geospeedometer and a geothermometer, if known. And so what we wanted to do was replicate the diffusion behavior that we saw in natural samples to determine those diffusion coefficients. And what we did was we did some experiments in the laser levitation furnace. Our starting material was a powdered natural tektite to which we added small quartz grains. And then we heated this material to temperatures between 1800 and 2400 degrees Celsius for times ranging from 1 second to 120 seconds. And the levitation gas was ultra high purity argon. And the video that you're seeing is an actual experiment. So this is a molten orb right now, and it's being heated in hopefully just a second. This is going to quench and we'll be able to see it cool into a glass. There we go. And now it's a glass and you could touch it with your finger. Oh, okay. So here I'm showing you some backscattered electron images of cross sections of the now cooled glass spheres that were heated in our experiments to 2200 degrees Celsius for varying times in the furnace. We can see that there's a textural evolution with time. So at 5 seconds, sorry, I keep losing my mouse. At 5 seconds here, some of the quartz grains, which are the darker gray regions, are still in the process of converting to Le Chatelierite. At 10 seconds, there's complete conversion. By 50 seconds, we have reproduced the Schlieren from the natural sample that I showed earlier. And in the longest experiment, we now see we're nearly vesicle free and also have significantly fewer Le Chatelierite. We determined those diffusion coefficients or diffusivities from these experiments, which were done at known conditions, and then compared the diffusion profiles to those observed in the natural tektites. And in this way, we were able to determine the thermal histories of individual tektites in the strewn field. And so we did this for tektites all over this strewn field. So this is a map showing you places where we were able to curate tektites from all of these areas that are marked with these symbols here. So we were able to measure profiles from the large layered tektites that I was telling you about earlier. And these are all collected up here in Indochina. And we found that they were heated to temperatures between 2000 and 2200 degrees Celsius for just a few seconds. And then we also compared diffusion profiles and diffusivities to a series of tektites that were collected from Indochina, these splash form tektites also in Indochina, the tektites from the Philippines, and also tektites all the way from Australia. And what we found was that these tektites all experienced similar thermal histories. They were all heated to temperatures between 2000 and 2200 degrees Celsius for between 20 and 50 seconds. And so our estimates of heating temperatures and durations show that splash forms were hot for longer than the layered tektites, but that there's no correlation with geographic location, which is a surprising result. We haven't measured any of the profiles from microtektites yet, but that will hopefully be done in the future. And so I want to just look back at this final shot from Artemieva's hydrocode model that I showed you the animation of earlier. And the results that we got offer possible temperature time pass for this molten material here. The yellow material is melt, and these will be future tektites. So if we were able to run this animation for much longer times than just 4 seconds here, we might envision what might happen to this tektite parent material. Some of the melt would fall to the ground first, relatively close to the impact site, and pool on the ground before cooling. And this forms those layered tektites. The rest of it would continue to travel away from the crater while entrained still in the hot vapor, which would buffer the melt temperatures for longer times until at some later time, the plume dissipates and those airborne melt particles cool very quickly and continue along their own ballistic pathways, landing in their final location. So they experience the same thermal history, even though they end up in very different geographic locations. So I'm going to shift and move on to the second study that I want to talk about. And at the end, we'll summarize it all together. So now we're going to be talking about how copper isotopes fractionate due to partial vaporization of melts at high temperatures. But why are we going to talk about copper? Why would we choose this element out of all elements? Well, copper is what we call a moderately volatile element, which means that it readily vaporizes at high temperature, but not completely. This is illustrated here in a tektite melt with green circles representing copper. Some of it will vaporize and convert to the gas phase at high enough temperatures, but some will remain behind in the melt. And this means that we can measure it later in a tektite sample, which is pretty important if we're going to be using it. Copper is also good for this study because it has two isotopes, copper 65 and copper 63, shown here. They have the same number of protons, but different numbers of neutrons, making copper 65 heavier than copper 63. Because of this slight mass difference, these isotopes are going to behave differently during vaporization. Specifically, the light isotopes, copper 63, shown in green, are going to preferentially leave the melt relative to the heavier copper 65, now shown in blue. As a result, we see that the ratio of copper 65 to copper 63 in the melt becomes higher than that in the gas as vaporization proceeds. This leaves behind a melt that has concentrated the heavy isotope of copper relative to its starting material, or parent rock. And this is the process known as fractionation. This idea is supported by data from the actual tektites. So before we look at the data in this plot on the right, I want to define what the x-axis is, in case you're not used to thinking about stable isotopes. So this is what we call delta 65 copper, which is the ratio of copper 65 to copper 63 in a sample relative to that same ratio in a standard. This is going to be a very small number, so we multiply it by 1,000 and report it in units of per mil, which is this funny looking percent sign here. Now we can look at the data in this plot. We can see that tektites are higher in delta 65 copper than the bulk silicate earth, which is represented by this gray bar here. So that's going to represent the parent material of tektites. So tektites have a higher 65-63 ratio than the stuff that they're made of, which is what we would expect for fractionation that is induced by vaporization. So much like in the first study I presented, we wanted to try and see what conditions could replicate the observations from natural samples in terms of the copper isotopes. So to that end, we did vaporization experiments using a synthetic basaltic glass that was doped with extra copper as the starting material. And we heated these spheres in the levitation furnace at high temperatures for seconds to minutes. And the video is showing melt being partially vaporized, which results in the light isotopes and volatiles being preferentially lost to the vapor, leaving behind a residue that is going to be enriched in those heavy isotopes. So now we can look at the results of these experiments. And that's what I'm showing here in this plot of copper concentration on the x-axis versus delta 65 copper on the y-axis. So here I'm comparing our experimental data, which is the orange curve that I'm just going to label with experiments there, with the natural tektite data, which are the red circles down there. Those are natural tektites. And then above are these theoretically derived curves for free evaporation of copper, copper oxide, and also copper sulfide. So these curves are derived based on ideal evaporation behavior as would occur in a vacuum. We can see that the experimental data predict more fractionation than what is seen in natural samples, and that the theoretical curves over-predict fractionation compared to both the experiments and also to the natural samples. So why do these differences exist? We think that this is the result of the effect of vapor pressure and interaction with the flowing gas on isotope fractionation. Before we talk about the concepts of vapor pressure and gas flow in the experiments, I want to look at an example of evaporation that you're likely more used to thinking about and may have some intuition for. So here we're looking at a cartoon showing some of the major factors affecting evaporation of water. We see that temperature plays a role. So the hotter the water, the more evaporation will occur. Surface area also does. More surface area, more evaporation. I want us to focus, though, on these last two factors. Next would be humidity. So here, higher humidity is going to mean less evaporation. So this would be our higher humidity situation. We're getting less evaporation. There's more water vapor in the air when it's more humid, which means that a water vapor molecule has a higher chance of hitting another one and maybe bouncing back to the surface of the water where it would recondense. This corresponds to the vapor pressure at the surface of the melt in our experiments, more specifically to the partial pressure of copper that is in the vapor phase at the surface of the melt. So let's move on to talk about wind speed. Wind speed also plays a role in evaporation of water here, with more wind leading to more evaporation. And this would correspond to the gas flowing around the melt in our experiments. So now that we have that framework, let's talk about it in the context of the experiments. There's a spectrum when it comes to evaporation behaviors, where on one end, you've got what we call ideal or free evaporation. This is where all evaporated particles are quantitatively removed from the melt such that no recondensation occurs. And this would be the case, for example, for evaporation in a vacuum. If this was happening in our experiments, it might look like this cartoon here that I've drawn, where all of the evaporated particles are being immediately and quantitatively carried away by the gas flow, such that they will not recondense back onto that melt. On the other end of the spectrum, we've got a situation where equilibrium between the gas and vapor exists. So in this situation, the evaporation and condensation rates are constant. And this is what would exist in a closed system where no material is escaping. Or if you want to think about our water analogy, at 100% humidity. Our experiments are somewhere between these two end members, as shown in the middle cartoon. What we are seeing here is a return flux, where some evaporated particles, while they will leave the melt, but then they bounce back and they recondense into the melt, while some are carried away. So in this scenario now, the evaporation and condensation rates are not constant. So the ideal free evaporation scenario represents a purely kinetic isotope fractionation, which would be larger than the fractionation that we see due to partial vaporization in our experiments, which would be larger than the fractionation that we would observe at equilibrium. These different degrees of fractionation and rates of evaporation versus condensation are dependent on the partial pressure of the evaporated particles at the surface of the melt. So think of it as the humidity of copper above the melt. In our purely kinetic case, the partial pressure is 0, which is lower than the partial pressure in our experiments, which is lower than the partial pressure at equilibrium, which would be saturation. The fact that we have some return flux in our experiments means that the partial pressure is greater than 0, or the effective partial pressure, to be more accurate. And thus, the fractionation will be suppressed relative to the purely kinetic case. And it would be greater than that for equilibrium, or a case where the surface of the melt is saturated. So let's look at the data again, now that we have that framework. We think about the differences among these trends as being due to the effect of vapor pressure and interaction with the flowing gas on isotope fractionation. So free evaporation that would occur in a vacuum would be a situation where the partial pressure is 0, which we just talked about. This would result in the highest fractionation, and that's what we're seeing here in the plot. If we look at where the experimental data lie relative to the other trends, we can interpret this as telling us that our experiments have a higher vapor pressure than that of a vacuum, but it's lower than that experienced by tektites in the vapor plume. So we can conclude that copper isotope fractionation in tektites is the result of vaporization in an impact plume with a relatively higher vapor pressure. And right now, we are currently working on a model to explain the complex role of gas flow on fractionation. And spoiler alert, it matters. I'm not ready to share that model yet because our paper is still in review. So check back in later. Maybe I can come out for an in-person talk and tell you about that. Turns out we can use isotope fractionation as a velocimeter as well as a, as a velocimeter. And so now I want to summarize both of the studies. So overall, we've learned that the aerodynamic levitation laser furnace experiments successfully simulate some features of impact glasses and can be used to learn about impact plume conditions. For the first study, diffusion in tektites, we've learned that estimates of heating temperatures and durations based on diffusion experiments show that the splash form tektites were hot for longer than the layered tektites, but that there's no correlation with geographic location. In the future, we will work to analyze more tektites from all of the stream fields and try to create thermal maps of those impact plumes. And then the second study that I discussed about vaporization-induced isotope fractionation, we learned that copper isotope fractionation in tektites is the result of vaporization in an impact plume with a relatively high vapor pressure than that produced in the experiments. Our future work is exploring the role of the relative gas melt velocity in an impact plume and in other scenarios, such as pebble accretion, on isotope fractionation. So let's go back to the initial question that I posed. Laser beams and levitating lava orbs, science fiction or real tools for studying planetary science? I hope you'll agree with me that the answer is that they are real tools for studying planetary science. I would like to take a moment to acknowledge all of my collaborators shown here who've contributed to the works that I shared with you today, as well as the funding agencies that allowed us to conduct these experiments and analyses. And then also, I would like to thank the Mineralogical Society of America and also Peter Busek for honoring me with being the inaugural Peter Busek New Directions in Mineralogy and Petrology lecturer.
I'm going to discuss how we would look for a new law. In general, we look for a new law by the following process. First, we guess it. Then we don't laugh, that's really true. Then we compute the consequences of the guess to see if this is right, if this law that we guessed is right, we see what it would imply. And then we compare those computation results to nature, or we say compare to experiment or experience. Compare it directly with observation to see if it works. If it disagrees with experiment, it's wrong. And that simple statement is the key to science. It doesn't make a difference how beautiful your guess is. It doesn't make a difference how smart you are, who made the guess, or what his name is. If it disagrees with experiment, wrong. That's all there is to it.
So I'll just end with this slide, advertising some of the great programs and services of the Mineralogical Society of America. And thank you for paying attention. And I would love to answer any questions